Hi everyone. So today we're following up the lesson on the normal curve and the normal distribution with something called the standard normal distribution. So this is just a specific type of normal distribution, and we're going to talk about why it's significant here in just a minute. Um, Standard normal distributions involve something called z-scores. But before we get into talking about how to calculate a z-score, I kind of want to do a quick example to kind of convince you of this. Why do we need to standardize distributions? So let's suppose that you are in a math class, okay? And in your math class, you score an 87 on the chapter test. Okay, that's your score. You got an 87. You know that the mean of your class is an 83 and that the standard deviation of your class is, I don't know, 4.5, we'll say. Okay? So you have that information about your math class. Now, this is on a percentage scale, so this would be like 87 out of 100. Now let's say that you go take a science test, and your science teacher doesn't grade things in percentage form. Okay, they just grade them out of total points. So maybe you got a 42 on that test, but it was really like, I don't know, a 42 out of 45 or something like that. And you know that in that class, the class average was a 40 with a standard deviation of 3. And you want to know, in which class did you do better? And I'm not just talking about better percentage-wise, like comparing these two, but in which class did you do better compared to the rest of your class? All right, in which class did you have a better performance than the other students in your class? Because there are a lot of situations in education, especially, and in life, when really what's important is how you did compared to everybody else and not necessarily just in terms of a percentage. But the problem is these are on two totally different scales. I've got two totally different sets of data here. And so it gets kind of hard to compare. So what we can do is we can think about this using that normal distribution thing that we talked about. So here's my math class. Okay. And so for my math class, I know that my mean was 83 and my standard deviation was 4.5. So this first standard deviation would be 87.5. And then I could go up another one and I could say, let's see, that would be 92. And then your third standard deviation would be 96.5. I'm only going to worry about that side of the curve. Okay. For my science class, here's what my class average is going to look like. My mean is at 40. Standard deviation is 3, so this is 43. This is 46. And this is 49. Okay. So in this class, if I were to think about where I fell with an 87, that would be just before this line, right? And with a 42, I would also be just before this line. So the question is, where did I actually do better? Where was I actually better compared to the mean? And so what I want to know is how many standard deviations does it take to get from here to here? I want to know what is this distance in terms of that standard deviation, because that'll give me a sense of how close I came to hitting that first standard deviation line. So let's think about how we could figure that out. I want to know how far is it from 83 to my score, which was an 87. So to find that, I'm going to take my score, 87, and subtract 83. And I'm going to get 4. Okay. Here, I'm going to take my score, which is a 42, and subtract that mean, which was 40, and get a distance of 2. But again, I'm not so concerned about my actual raw score here. I want to know in terms of standard deviation, which one of these got me further away from the mean? Which one of these did I outperform the class more? I guess is a better way to say that. So then what I want to do is say, okay, in terms of that standard deviation, how far did I go? So I'm going to take this distance of 4 and divide by the 4.5 for my standard deviation. Okay. And let's see, 4 divided by 4.5 is going to be like 0.8. I think it's 0.8 repeating. Okay. Here on this one, 42 divided by 40, and I'm going to divide by my standard deviation of 3. And I'm going to get 0.6 repeating. Okay. So that tells me that this one was actually a little bit further away from the mean, meaning in comparison to the rest of the class, my math score was actually a little bit better than my science score was, okay, in terms of the data that I'm given here. So this was just an example with 2 made up scores, okay? I just made up 2 different situations where if I wanted to compare my performance in this class to my performance in this class, this is the process I would go through. And really what this z-score represents is the number of standard deviations above the mean that my data point falls, okay? But this gets really important when we start talking about things like standardized tests. And this is really where the name standardized tests comes from. Is you're not concerned about what your percentage is on a standardized test. You're concerned with how did you perform compared to everybody else. And probably somewhere in the data that they give you, you can find how many standard deviations or what your z-score is, meaning how far above or below the average did your score fall. So you can kind of compare yourself to the rest of the people who took the class. The use of this normal curve is what makes it be a standardized test. So let's go back to our notes here for a second. So why do we need to standardize distributions? If you just want to jot something down here, it's to be able to compare data from different data sets. Whoops. Different data sets. So you can take a value from one data set and compare it to a value in another data set and still get a sense of where the 2 data sets fall. That calculation that I did back here, where I figured out how many standard deviations above the mean were each of these scores, that was finding a z-score. Okay, so this thing right here that I came up with, that is what's called a z-score. So technically the definition of z-score is the number of standard deviations above or below the mean. And that above or below is really going to be indicated by whether it's positive or negative a data point is. Okay, so the z-score really tells you number of standard deviations above or below the mean. And if you think about this calculation that we did, I'm going to come back to this again. What we did is we took our raw score, right? So that came from my score. We're just going to call that X. And we subtracted the mean, which we use mu for, okay? And really what that did is told you just your raw distance from the mean. And then we divided by the standard deviation to figure out, to divide it into those standard deviation chunks, okay? So our formula for z-score, and you will want to know this formula, is always the data point minus the mean divided by the standard deviation. That's how we're going to calculate a z-score. Okay, so maybe this example I think will speak to you a little bit more because it's a little more relevant to you. Maybe not this year, but. So Jacob scores a 16 on the ACT and Emily scores a 670 on the SAT. So these are 2 different tests, 2 different scoring methods. Assuming both tests measure the scholastic aptitude, who has the higher score? Who did better here? Who's sitting in a better place? And then it gives me my mean and standard deviation of the SAT and mean and standard deviation of the ACT. So what I want to do is convert these both into z-scores, because once these things are in terms of z-scores, I can compare the 2. So if I'm looking at Jacob, I'm going to take his score of 16 and subtract the average on the ACT, which is 20.8. And then I want to know what does that distance equate to in terms of standard deviation. So I'm going to take that and divide it by 4.8. I can tell this one is going to be negative because his score is below the mean, right? So we're going to go, oops, 16 minus 20.8. Notice I use parentheses there, and then divide by 4.8. So negative 1. So that tells me that Jacob is 1 standard deviation below the mean. If I'm looking at a normal curve, he is 1 step to the left. Let's look at Emily. Okay, so Emily's score on the SAT was a 670. Okay, I'm going to subtract the mean of 1026. That gives me how far away from the mean she is. And then I want to think about that in terms of standard deviations, if I'm counting standard deviations. So I'm going to divide by the 209. Hers is going to come out negative 2, it appears. 670 minus 1026 divided by 209, and I get negative 1.7. So she's almost 2 standard deviations below the mean. So if we're being totally honest here, neither Jacob nor Emily did very well here because both of them are below average, right? But if I had to pick one, if I had to say, okay, grab the person who got the higher of the two, that would be Jacob, okay? Jacob did less terribly than Emily did, okay? Because he is 1 standard deviation below the mean. Okay, so let's look at example 2. And this is kind of what I was trying to point out with that first example I did, that you may have different scoring methods here. So this is a student score in 4 different classes. This gives you an idea of class average and standard deviation. So basically this is mu and sigma, right? And this is like your x value. And so what I want to do is convert each one of these to a z-score to figure out which one of these kids actually did the best. So let's say this is 4 different math teachers that all have different grading systems. So this teacher, I would bet, is grading on just a percentage scale. This person looks like they're grading out of, I don't know what the highest score would be, but I don't know, maybe 30 points or something. This one hopefully is grading out of maybe 15 or 16 points. This one also looks like a percentage to me, but I want to know which one of these kids actually did the best compared to each other, okay, and compared to the rest of their class. So I'm going to do each one a z-score, and I'm not even going to write these all down. I'm just going to start calculating. So I'm going to do 80 minus 75. That's what's going to tell me I'm 5 points above average. And then if I'm talking in terms of standard deviations, I can divide by 10 and get a 0.5. So student A was half a standard deviation above the mean. Student B, 28 minus 25, divide by the 4. And this student was 3/4 of a standard deviation above the mean. This one I probably don't even need a calculator for. I didn't on the last one either. But 13 minus 12 is 1. All right, and the standard deviation is 1, so 1 over 1 would give me a z-score of 1. This student is 1 standard deviation above the mean. And then on this next one, 98 minus 92.4, divide by 6.3, and this student is 0.8, repeating standard deviations above the mean, okay? So if I had to pick which student did the best in comparison with the rest of their class, it would be this guy right here, because he's 1 full standard deviation above the mean, okay? And then this student would be next, this student would be next, and this student would be last, okay? But all of them scored above average, so, I mean, that's something. That's better than Jacob and Emily back here. But that's all a z-score is figuring out how many standard deviations above or below the mean you are, because once we're talking in terms of the number of standard deviations, it's easy to compare one data set to another. Okay, that's really it for this part of the lesson. There will be another video coming up shortly with the second part.